Good morning, everyone. Welcome. I want to thank you for joining us for episode 43 in the Gleeble webinar series. My name is Dan Quigley, and as always, it's my pleasure to welcome you to our little corner of the internet where the Gleeble community of researchers can share and learn. We know how valuable your time is, so we really do appreciate you spending time with us. We've really gotten great feedback from the research community, and people are finding value in these webinars. So we do appreciate you being here and learning and sharing. So thank you to those that are just joining us here, and then also those that have presented or are scheduled to present in the future. We all do appreciate it. Today's presenter is Ilchat Sabirov from IMDEA Materials Institute in Spain. Ilchat has been a longtime Gleeble user, and his group have been publishing a lot of really great high-quality papers for a long time, and we always appreciate seeing the Gleeble work that has been featured in his work. So appreciative of him and his time for putting this presentation together, and his team as well. The title of today's presentation is Physical Simulation of Investment Casting, and as many of you know, the development of investment casting processes has been a challenge for manufacturers of complex shaped parts. Typically, numerous experimental casting trials are carried out to determine the optimum casting parameters for fabrication of high-quality products. The team at IMDEA have developed a new tool for physical simulation of investment casting. It consists of thermal model and melting and solidification experiments on their Gleeble 3800. The thermal model is employed to predict local cooling rate during solidification at each point of a casting. Melting and solidification experiments are carried out under controlled cooling rates estimated by the thermal model. The team has developed special ceramic tubes fabricated from the material used for the manufacturing of ceramic molds for investment casting. The melt is contained in the ceramic tube, which is heated to the temperature of ceramic mold in investment casting. Dr. Sabirov will compare the outcomes of physical simulation and how they are validated against experimental results. And it's shown that phase composition, secondary dendrite arm spacing, grain size and shape of carbide particles, local microhardness, and skin thickness can be predicted at each point of the casting via physical simulation. As always, it's our goal to keep this webinar to 1 hour or less. We will have time for a live Q&A at the end of the presentation, so if you have questions, please submit them using the chat feature here in the webinar software. We'll review those questions at the end of the presentation, time permitting, with Dr. Sabirov. Video of this presentation will be available online soon, and certificates will also be emailed to you if you're listening to this live. You'll also be able to find a link to this video as well as videos of past webinars by going to our website at gleeble.com and then click on the resources link in the top navigation bar. Once there, click on webinars, and there you can view past webinars and sign up for future webinars. Our next webinar will be held on September 23rd. We'll be posting a registration link to that webinar shortly on our website, and you should also get an email with that notification as well. But if you can, just save that date, September 23rd, same time and same place. Without further delay, it is my pleasure to hand this over to Dr. Sabirov. I will play that in a moment.
Thank you very much for introduction, Dan. So my presentation is about physical simulation of investment casting, and this research was carried out at IMDEA Materials Institute in collaboration with industrial partners and university within frame of a project New Generation Nozzle Guide Vanes, OneCast, funded by Aranet Matra Plus. It is a part of thesis of Mehdi Rahimian, who was co-supervised by me and Dr. Sergeant Milenkovic, and also by Professor Javier Yorca. We have collaborated with colleagues from Precicast Bilbao, a company which is now a part of ITP Aero, with Laura Maestro and Aitor de Avila, with colleagues from Calcom ESI. It is a company developing software for simulation of casting processes, such as Procast with Ole Kosser and Loic Calva, and with the University of Applied Sciences and Arts, Western Switzerland, with Agustin Taroba and Professor Frank Carreño Marelli. In Gleeble community, we know that there is a well-developed tool for physical simulation of continuous casting. Continuous casting is a process where molten metal is solidified into a slab for subsequent rolling in the finishing mills. This physical simulation tool is based on melting solidification experiments in a Gleeble simulator. So we make a sample from the material, we weld the thermocouple to the midsection of the sample, we put a a quartz tube onto it, we cover it by copper grips and put this setup in a Gleeble chamber where we perform melting solidification experiment. We melt the midsection and then we cool it down in a well-controlled manner, simulating continuous casting process. This method has been applied to many metals and alloys, and in literature there are many articles describing experimental results from such experiments. Investment casting is very different from continuous casting. Investment casting is usually used for manufacturing complex shape parts which cannot be produced via thermo-mechanical processing, via rolling, forging, or extrusion. Investment casting process consists of many steps, and the first step in investment casting is to manufacture the wax pattern tree for the process. This is done by attaching the wax patterns of complex shaped parts to be manufactured to a wax bar, which serves as a central sprue. Also, a ceramic pouring cup is attached to the end of the bar. This setup is called the wax pattern tree. And now this tree is dipped in a ceramic slurry. So a ceramic layer is obtained over the surface of the pattern, and then this pattern is repeatedly dipped into the slurry to increase the thickness of the ceramic coat. Once the refractory coat is thick enough, it is allowed to dry in air in order to harden, and then the obtained setup is heated to elevated temperatures in order to melt the wax, which flows out of the mold, leaving the cavity for the metal casting, or leaving the hollow ceramic shell. So then this ceramic mold is heated to high temperature, and then the molten metal is poured. This molten metal fills in the interior of the hollow ceramic shell, and after solidification and cooling, the ceramic mold is broken and removed, and the obtained complex shaped parts are subjected to surface finishing and to additional heat treatments if necessary to reduce the residual stresses or to modify the microstructure. As one can see, this is a very complex processing route, and the investment casting results in a very inhomogeneous microstructure over the complex shaped parts, since the solidification conditions vary significantly due to complexity of shape of these parts, and also often investment casting of complex shaped parts with thin elements results in formation of misruns. A misrun occurs when the molten metal freezes before it reaches all parts of the mold cavity. Therefore, it is important that we prevent misruns from occurring during investment casting. So, in this the main objective of this project was to predict microstructure at each point of the as-cast nozzle guide vanes, which are produced via investment casting process. The common material for manufacturing these complex shape parts is a Inconel 718, and here it was produced using a MAR M247 nickel by super alloy, which can show a better mechanical performance at higher temperatures. And a good performance at high temperatures is important because nozzle guide vanes direct the airflow onto the turbine blades, and also at the same time they convert pressure energy into kinetic energy. So it means they can they're subjected to high temperatures during their service life. So in order to perform a physical simulation of the investment casting process, we need an information on the range of cooling rates which take place during solidification of this complex shape part. So a calculation of the cooling rates was performed by our industrial colleagues from Qualcomm SE. So they developed a mesh representing the shell mold, and they also using Procast software. They also modeled the filling of the mold and solidification process, and the local cooling rates were calculated for each point of the nozzle guide vane. And the obtained results, the obtained theoretical results, were experimentally validated via real investment casting of nozzle guide vane, where the thermocouples were fixed to different spots of the complex shape part, and temperature time plots were recorded during the investment casting process. So the theoretical results have shown that cooling rate during solidification and cooling process varies in a wide range from 0.25 degrees per second to 10 degrees per second. The lowest cooling rates correspond to the thickest parts of the nozzle guide vane, which are close to the gate, and the highest cooling rates correspond to the thinnest elements of the nozzle guide vane. So, and here one can see two typical temperature time plots are theoretically estimated for 2 points of the nozzle guide vane, which are cooled at 0.25 degrees per second and 1 degree per second. So this and this point. More details about development of this Procast model and its validation can be found in this joint article published with our partners. So in the second step, our industrial partners from Precicast Bilbao have prepared ceramic tubes for melting solidification experiments using this wax pattern. So these tubes were prepared using the same ceramic slurry, which is used for manufacturing real ceramic shells for real investment casting process. So, and the obtained tubes are shown here on this image. So for the melting solidification experiments, we machined the samples of a standard geometry. So the controlling thermocouple was welded on midsection, and the ceramic tube with a slot was put onto a sample, and the sample was covered by copper grips. So looks the setup before the experiment. It was introduced into Gleeble chamber, and the sample, the midsection of the sample, was heated to the temperatures between 1355, 1360 degrees. So the midsection of the samples was molten. So, and after full melting of the midsection, the cooling was performed in a very well controlled manner with different cooling rates. And on this temperature time plot, two curves are shown from melting solidification, from solidification experiments with cooling rates of 0.25 degrees per second and 1 degree per second. And one can see that the cooling rate was very well controlled during the experiment. So the processed samples were cross-sectioned, and their microstructure was thoroughly analyzed. Also, in parallel, samples were cut from the real as-cast nozzle guide vane from the areas which cooled down with similar cooling rates, 0.25 and 1 degrees per second. So, and the microstructure of the Gleeble samples and samples from real nozzle guide vane were compared. So on this slide, the dendritic structure of all samples is compared, and we know that the secondary dendrite arm spacing has a strong effect on strength of nickel-based superalloys. One can see here that the morphology of the dendritic structure in the Gleeble sample is very similar to that of a nozzle guide vane sample, and the values of secondary dendrite arm spacing, they nearly coincide. If we increase the cooling rate to 1 degree per second, it results in refinement of dendritic structure, which is also well predicted by physical simulation. We can see a finer dendritic structure and also much lower secondary dendrite arm spacing, which is close in the Gleeble sample and in the sample machined from a real nozzle guide vane. Now let's have a look at the grain structure of the samples. We can see that physical simulation can reproduce well the grain structure to the average grain size values in Gleeble samples and in real nozzle guide vane are very close, and they decrease with increasing cooling rate. Now let's compare the phase composition of the samples. Nickel-based superalloys are characterized by formation of the gamma prime eutectic tools, which can degrade mechanical performance of the alloy. This gamma prime eutectic is a non-equilibrium solidification microconstituent, and its formation is controlled by chemistry of the alloy and cooling rate. Here we can see that physical simulation can very well predict the volume fraction of the gamma-gamma prime eutectic and average size of eutectic pool. These values are very close to each other, and with increasing cooling rate, these values are significantly reduced. That is also well reproduced by physical simulation. Now let's compare morphology of carbides. We know that their morphology and volume fraction can strongly affect the strength and creep resistance of nickel-based superalloys. We can see that physical simulation reproduces very well the morphology of carbide particles at both cooling rates. Three types of carbides can be revealed in both Gleeble samples and samples after real investment casting. So those are blocky carbides, carbides having irregular morphology, and script-like carbides. So with increasing cooling rate, we can see that the size of carbides is that the carbides are refined, and also interparticle spacing increases. This observation can be explained by a decrease of time for diffusion of alloying elements. In other words, by a decrease of carbide growth time. Since carbides are formed at interdendritic areas, the refined dendritic structure is at higher cooling rate reduces the interparticle spacing, which is also very well reproduced by physical simulation. So we can conclude that combination of thermal model and Gleeble melting solidification experiments, followed by thorough microstructural characterization of Gleeble samples, allows to precisely predict microstructure at each point of the casting. And this is a very valuable information. So how it can be used? For example, we want to dissolve the gamma-gamma prime eutectic pools in the as-cast part via heat treatment. The larger the gamma-gamma prime eutectic pools are, the longer treatment is required. Based on the available information on the largest eutectic pools in the casting, we will select the optimum heat treatment parameters which will allow to dissolve the largest eutectic pools in the microstructure and to produce a high quality part. So next part of my presentation focuses on physical simulation of skin formation during investment casting. So as I have already mentioned, misruns can occur during investment casting process when the molten metal freezes before it fills the interior of the ceramic shell. This effect is often observed in the case of casting of complex shaped parts with very thin elements. So misruns usually happen if ceramic shell is not hot enough. So nickel-based superalloys, they have a very high melting point, which is well above 1300 degrees. But the ceramic shell cannot be heated to high temperatures since it degrades at temperatures above 1100 degrees. So also the manufacturers usually try to keep temperatures as low as possible since high temperatures increase processing cost. Therefore, we need to determine an optimum temperature of ceramic shell for casting given complex shape part, which would allow us to avoid misruns. This is often done by a trial and error approach, and which consumes a lot of resources. And to try to solve this problem, we have developed the next physical simulation tool, where we use the same sample of the same sample, so the same geometry, the same ceramic tubes made of the same material, which is used for manufacturing real ceramic shells for the real investment casting process. Now, in these tubes, we drill a hole and we place in the midsection of the tubes, and we place a thermocouple inside of this hole. So it is very close, the end of the thermocouple is very close to the inner surface of the ceramic tube, or in other words, it is close to the hot sample. So we weld the controlling thermocouple to the sample, and we run melting solidification experiments. Ceramic tube cannot be heated via resistance heating because it's not conductive. But it can be heated via heat transfer from hot sample. So varying heating rate and contact time between sample and ceramic tube, we can reach the temperature of interest in the ceramic tube. So for example, in the given case, we reached the temperature of interest 1030 degrees in the ceramic tube. The longer contact time would allow us to reach a high temperature, and the shorter contact time, of course, would result in a low temperature of the ceramic tube. So we can vary the temperature of ceramic tube. Once the temperature of interest is reached in the ceramic tube, we allow the molten midsection of the sample to solidify, again in a well-controlled manner. So in these experiments, they were cooled down with the same cooling rates, 0.25 and 1 degree per second. And the processed samples are again cross-sectioned and characterized. So now let's compare the skin formed during investment casting of the Gleeble samples and skin formed during investment casting of a real nozzle white vein in the area which was cooled with the same cooling rate. So again, we look at two different cooling rates of 0.25 and 1 degree per second. So one can see that at the lowest cooling rate, we have a thick skin in the real in the sample from a real nozzle white vein, and the physical simulation well reproduces the skin morphology and also the thickness of the skin. We have 95 and 92 microns. With increasing cooling rate, the thickness of the skin somewhat decreases, and again, this decrease is also well reproduced by Gleeble. So now let's have a look at the morphology of the skin So from these SEM images, we can see that skin does not have any gamma prime eutectic tools. We don't see them neither in Gleeble samples nor in the samples made from real nozzle white vein. So also the same, no gamma prime eutectic pools are observed in the samples after cooling with the cooling rate of 1 degree per second. So, and finally, if we look at high magnifications, at the gamma prime microstructure of the skin, we can see that physical simulation very well reproduces the gamma prime microstructure. And we, in both cases, in the case of the Gleeble samples and the real nozzle white vein, gamma prime particles show average size of 0.5 microns after cooling with the lowest cooling rate, and increasing cooling rate to 1 degree per second results in a finer gamma prime particles having an average size of 0.35 microns, which is very well reproduced by physical simulation. So from these results, we can see that the developed tool for physical simulation of investment casting of complex shaped parts allows to predict thickness of the skin and its microstructure as a function of cooling temperature and temperature of ceramic shell. And the predicted skin thickness can be used to estimate risk of formation of misruns during investment casting of complex shape parts. If skin thickness is close to the thickness of thin elements, then there is a high risk of misruns because the molten metal will fully solidify, not having filled the interior of the thinnest elements of the ceramic shell. So, and these are the general conclusions to this presentation. So one can see physical simulation can be used to reproduce investment casting at small scale. It allows us to predict with very high accuracy a complex microstructure formed at different parts of complex shape parts produced via investment casting. And it also allows us to predict the thickness of the skin depending on the temperature of a ceramic shell. And application of a physical simulation tool can greatly save cost and time required to develop novel investment casting rods. So thank you very much for your attention. And if you have any questions, I will be glad to answer them.
Great. Thank you very much, Ilchat. That was a great presentation. What I'll do now is I'll share my screen with your presentation up there. We do have some time for a Q&A. Ilchat, can you confirm that you can hear me and we can hear you?
Yes.
Okay, great. All right. Again, thank you. Great presentation. We have a handful of questions that did come in during your talk. If you want me to go to any of the slides, let me know, and I can bounce around and get to that slide. Okay, so actually the first one was really more of a comment than a question. I think there was people were impressed at the how accurately the experimental results, the experimental test matched real casting. So I think that was impressive. So I think a lot of people on the call are Gleeble users, so diving into the actual experimental setup is interesting. So one of the questions was standard Gleeble testing methodology relies on kind of a visual confirmation that the material is melting. It's why we use the clear crucible, that quartz crucible that we use. So how did you confirm that the material had fully melted, given the mold that you used?
Dan, could you please go to the third slide? I think it was third slide. Yeah. So,
Okay.
No, the slide before.
There? Okay.
There you go. Yeah. Thank you. But we started this experimental work with the traditional melting solidification experiments using, just let me, okay, sorry, I don't have the pointer. Using standard quartz tubes, like in
right.
Performing standard melting solidification experiments using a standard quartz tubes. So, and the idea to use the ceramic shells, we got to that idea later. So by that time, we have already accumulated significant amount of knowledge on the melting solidification behavior of this material. And we perfectly knew that when we are temperatures above 1355 degrees, the midsection of the sample is fully molten. Also, when the material is not fully, the material fully molten and solidified samples which are fully molten and solidified, they look quite different to the samples which were just partially melted and solidified. One can see it during microstructural characterization. So in all our tests, the material was fully molten and solidified in the midsection.
As you mentioned, that the experimental test did match the real casting, so it probably has high confidence that it is fully melted.
Yeah, and also the photo, which is presented on the right side, it represents the melting solidification experiment from MAR M247 using quartz tube.
Okay. Very good. So another question was, did you use superheat? Did you go and how did you determine, if you did, how did you determine how high to go?
No, we did not try to do it.
Okay. Well, again, you were matching a real world casting, so maybe you didn't need to.
Because the risk of thermocouple detachment with increasing temperature increases, and well, we tried it, but we were not successful.
Okay. I have also heard that some people will apply, once it's melted, they will apply some compression. I believe that is to make sure that the molten area, the molten material fills the cavity. Did you need to do that at all? Did you have voids in your melt?
Yeah, we did some shrinkage porosity. It also took us a few, we applied a compression to compensate the thermal contraction during solidification and cooling process. And it took us a number of tests to find out the right compression speed in order to compensate the thermal contraction without damaging the microstructure.
Sure. Okay.
So we could find experimentally the optimum compression speed in order to compensate the thermal contraction without damaging the microstructure, and we applied that speed in our experiments.
Okay, great. We had a couple of questions about thermocouple types and how you affix them, and then as the questions came in, you actually did a very good job of describing them on the slide. So I think we'll skip those questions. I think those you did a great job describing how the thermocouples are used, and it was R and K type thermocouples in different locations. So I'll skip those questions. Again, I think they were already answered. We had a question here. It said, how did you account for the directional solidification in the Gleeble samples due to the thermal gradient? And is texture a major concern with this material? And let me know if you'd like me to jump to a slide.
Well, of course, we cannot measure the temperature gradient through the radial section of the samples. But from my feeling of from impression I have from microstructural analysis of samples, so the samples molten and solidified in ceramic tubes. They showed, how to say, the samples which were molten and solidified using a quartz tube. They showed more directional solidification along the axis of the sample. And in the case of the samples molten and solidified in ceramic tubes, we had already skin along the sample, also in the midsection. We did not have that skin just in the top part of the sample where we had a ceramic slot, so skin could not form there. We had skin formed in the midsection of the sample, and the solidification process started already also on that skin. So in the case of the samples molten and solidified using ceramic tubes, we have mainly solidification direction grows along the axis of the samples, whereas in the case of the samples molten and solidified in ceramic tubes, it is more like a how to say, the crystal, the grains are formed and grow not only at the edges, at the ends of the molten section on site edges of the molten section, but also on the at the bottom and of the sample. I don't know if I could explain it.
I think that was great. We only have 2 more questions, but one of them might be a big one, and maybe it would be a whole topic for a separate webinar. It says, what kind of differences are there between physical simulation of investment casting and physical simulation of standard casting?
Yeah, the main difference is that using ceramic tubes, we can physically simulate skin formation in the material. So that is something that we cannot do using a standard melting solidification experiments using quartz tube. So I think that is the main difference between these two types of experiment. And the information on the thickness of the skin is very valuable information because it allows us to assess the risk of misruns during investment casting.
Okay, great. Last question, and you may not have looked at this, but it says, have you applied this technique to microstructural prediction of new casting materials and geometries?
No, we haven't done it.
Okay. Well, this is great. I think that is all of our questions. A couple came in. I think they were already answered. So again, Ilchat, I really do appreciate you spending time. I know it takes a lot of time to prepare for the presentation and also sharing this information. So thank you very much.
Thank you very much for the opportunity to present.
Great. If anyone out there does have more questions for Dr. Sabirov, or if you would like to connect with him directly, please do reach out to me. I think everyone on here probably has my email address, but you also probably have a bunch of people at DSI's contact information. Reach out to any one of us. We'll be happy to connect you with Dr. Sabirov. If you have any technical questions about the operation of your Gleeble, please contact our service team. I think this is our 43rd webinar. I mention this probably every time, but we do have a new service portal that has a knowledge base and a service ticketing system. So current customers can go and create an account. You can click on the resources link in the top navigation bar at Gleeble.com, and then click on customer support portal. I will ask that you use your company or your organizational email so we can confirm that you do own that Gleeble, you work with that Gleeble. And then once you're in there, you can access that information, and that really is the best way to schedule service and support As you can imagine, it is challenging for our team to get out and visit people given the pandemic. They are doing their best, and as things open up, things will get very busy, and they will be in high demand to get on site. So please do plan ahead, connect with them, but also please do be patient. It is difficult to travel, and our number one goal is to keep everyone safe. So we want to keep our service engineers safe, our team safe, and also your team safe. So we want to make sure that we're traveling and doing it the right way. So, but again, use that service portal to access service and support. If you have any questions about how a Gleeble can support your research, please email anyone on our team. We can connect you with an application expert or someone in your region that can help connect you and work on that information for you. I want to thank everyone for joining us, and please do stay safe and healthy out there. Have a great day.